This is the first of a series of videos on programming language semantics, and in particular on the semantics of cool. Before we dive into the technical details, though, I wanted to spend a few minutes talking about what programming language semantics are and why we need them. The problem we have to address is that we need some way to say what behavior we expect when we run a cool program. So for every kind of cool expression, for everyone, we have to say what happens when it's evaluated. And we can regard this as the meaning of the expression. We somehow give rules that specify what kind of computation a particular expression does. And I think it's useful to look back and see how we dealt with this, with similar problems in defining other parts of cool, okay, the earlier things that we've looked at in this course. So for example, for lexical analysis, we defined a family of tokens using regular expressions. And for the syntax of the language, we use context-free grammars to specify the structure of how words could be strung together to form valid sentences in cool. And then for the semantic analysis, we gave formal typing rules. And now we're to the point where we have to talk about how the programs actually run. And so we have to give some evaluation rules. And these are going to guide how we do code generation and optimization. They're going to determine what the program should do and what kinds of transformations we can do on programs to make them run faster or use less space, or any other kind of optimization that we would like to perform. So far we've been specifying the evaluation rules somewhat indirectly. We've been doing it by giving a complete compilation strategy down to stack machine code, and then we've been talking about the evaluation rules for the stack machine, or actually translating the stack machine code into assembly code. And that is certainly a complete description. You can take the generated assembly code and go and run it on a machine and see what the program does, and that would be a legitimate description of the behavior of the program. And the question then is, why isn't that good enough? Why isn't just having a code generator for the language, why isn't that already a good enough description of how the code is supposed to be executed? And the answer to that is maybe a little hard to appreciate without having written a few compilers. But in a nutshell, people have learned through hard experience that assembly language descriptions of language implementations have a lot of irrelevant detail. There's a lot of things that you have to say when you give such a complete executable description that was not necessary to say about how the program executes. So for example, the fact that we use a stack machine, that's not intrinsic to the implementation of any particular programming language. There are other code generation strategies that we could have used. So the fact you don't have to use a stack machine to implement the language. Which way the stack grows, whether it grows towards high addresses or low addresses, you could implement it either way. The exact representation of integers, the particular instructions that you use to execute or to implement certain language constructs. All of these things are one way, or one particular way to implement the language, but we don't want them to be taken as the only way that the language could be implemented. So what we really want then is a complete description, but one that is not overly restrictive, one that would allow a variety of different implementations. And when people have not done this, when people have not tried to find some relatively high-level way of describing the behavior of languages, they've inevitably gotten into the situation where where people just have to go and run the program on a reference implementation in order to decide what it does. And this is not a very satisfying a situation, because often the reference implementation is not completely correct itself. It'll have bugs, and there'll be artifacts of the particular way it was implemented that you didn't mean to be part of the language, but because there's no better definition, wind up becoming fixed and sort of accidents of the way the language was implemented the first time. So there are many ways to actually specify semantics. In this video, we're going to begin our discussion of formal operational semantics. Just as we did with lexical analysis, parsing, and type checking, the first step in defining what we mean by a formal operational semantics is to introduce the notation. And it turns out that the notation we want to use for operational semantics is the same or very similar to the notation we use in type checking. We're going to be using logical rules of inference. So in the case of type checking, the kinds of inference rules we presented prove things of the form that in some context we could show that some expression had a particular type, in this case the type C. And for evaluation, we're going to be doing something quite similar. We will show that in some context, now this is going to be a different kind of context than we had in typing. So this is going to be an evaluation context as opposed to a type context, and so what goes in the context will actually be different. But for the moment, all that really matters is there's some kind of a context, and in that context, we're going to be able to show that some expression evaluates to a particular value v. So as an example, let's take a look at this simple expression, e1 plus e2. And let's say that using our rules, which I haven't shown you yet, but let's say we had a bunch of rules, and we could show that in the initial context, that e1, in that same context, okay, so these contexts are going to be the same, that e1 evaluated to the value 5, and e2, also in that same context, evaluated to the value 7, then we could prove that e1 plus e2 evaluated to the value 12. And if you think about it, what this rule is saying is that if e1 evaluates to 5 and e2 evaluates to 7, then if you evaluate the expression e1 plus e2, you're going to get the value 12. And now what's the context doing? Well, it doesn't do a whole lot in this particular rule, but remember what the context was for in type checking. The context was for giving values to the free variables of the expression. And so we need, for an expression like e1 plus e2, to say something about what the values are of the variables that might appear in e1 and in e2 in order to say what they evaluate to, and therefore to say what the entire expression e1 plus e2 will evaluate to. Now, let's be a little more precise about what's going to go in the context. So let's consider the evaluation of a expression or a statement like y gets x plus 1. Okay, so we're going to assign y the value x plus 1. And there are two things that we have to know in order to evaluate this expression. First of all, we have to know where in memory a variable is stored. So for example, the variable x here, we're going to have to go and look up x's value and then add 1 to it. And then that value is going to have to be stored in whatever memory location holds the value for y. Okay? So there is a mapping from variables to memory locations. Okay, and that is called, in operational semantics, the environment. And this is a little confusing maybe because we've used environment for other things. Okay, so now let's forget about those other uses of the word environment. When we're talking about the operational semantics, what the environment means is the mapping, the association between variables and where that variable is stored in memory. And then, in addition, we're going to need a store, and that's going to tell us what is in the memory. So just knowing the location for a variable isn't quite enough. If we know the value of x, if we know the location for x, for example, well, that's important because that's where we're going to get the value of x, but we also have to know exactly what value is stored there. And so a store is going to be a mapping from memory locations to values. These are the values that are actually stored in the memory. So it's two levels of mapping. We associate with each variable a memory location, and then each memory location will have a value in it. So now let's talk about the notation that we're going to use for writing down the environment and the store. So as we said, the variable environment maps variables to locations, and we're going to write that out in the following way. We're going to just have it as a list of variables and location pairs separated by a colon. So this environment, for example, says that variable A is at location L1. In the next couple of videos, we're going to be looking at the details of the cool operational semantics, going over the semantics of each individual kind of expression. We'll start with the easy ones and work our way up to the more complicated ones. So the easiest rules are the rules for the constants in cool. So the value true, the expression true, I should say, evaluates to a Boolean with the value true. And it doesn't modify the store, so the store is unchanged because it doesn't do any updates, obviously. And there's a corresponding rule for false. And integers are very, very similar. So if a integer expression, integer literal I, will evaluate to an integer object with the value I, and again, the store is not modified by such evaluation. And finally, strings. If S is a string literal of length n, then it will evaluate to a string object with the properties n and the string constant s. The evaluation of identifiers is very straightforward given that we have both an environment and a store. So to evaluate an identifier, and this would be a variable name like x or y or foo, what do? Well, first we look up in the environment where that identifier is stored. So that will give us back a memory location, L, sub ID in this case. And then we look up in the store what the value is at that memory location. So we use the same memory location here as an argument to the store to get back the value that variable currently has. And notice that just a reference, this is a read of memory, so this is loading, you can think of it as loading the value of the variable. This does not affect the store, so the store is the same before and after. This is just looking up the value of a variable, not updating the variable. The expression self just evaluates to the self object. So this is a place where we just make use of the fact that the self object is part of the environment. So that just gets copied over here as the result of the expression. And notice again that the store is unaffected by the evaluation of self. Now let's see how a slightly more complicated expression is evaluated, in particular the assignment expression. So an assignment consists of two parts: an identifier that is being updated, and an expression that is going to give us the new value. So for example, just to remind you, we might have something like x gets 1 plus 1. So 1 plus 1 here would be the expression e, and x would be the identifier. All right? And so in order to evaluate the assignment, the first thing we have to do is we have to know what value we're going to be writing into the identifier. So what is the update we're going to perform? So the first thing to do is to evaluate E. Okay? And notice here that E is evaluated in the same environment. So it has the same three components here as here. All right? So it just says the first thing we do is we run E. Okay, and that's going to give us back a new value V, or going to give us back a value V, excuse me, and possibly an updated store. So E can be an arbitrary piece of code. It could itself have assignment statements in it, and so the store that we get out might be different. All right, so E produces a value V and an updated store S1. And now, to actually do the assignment, what do? Well, we have to know what memory location we're supposed to update. So we look up the memory location for ID, and that'll give us some location L sub ID. And then we modify the store with the new value. We modify the store at that point with the new value. So we replace the location LID, or we update the value at the location LID to be the value of E, the value V. And we do that in store S1, which gives us a new store S2. And now notice that S2 is the store that results from the evaluation of E. Okay, so after we do the assignment returns the value V, which was, of course, the value of running E, and it returns the updated store S2. Next, let's talk about the operational rule for addition. So to evaluate E1 plus E2, what are we going to do? Well, first we're going to evaluate E1, and notice that that is done in the same context as the context of the entire expression. Okay, so the components of the context here for evaluating E1 are exactly the same as the components for the overall expression E1 plus E2. So when we evaluate E1, it's going to give us a value V1, and it's also going to give us an updated store S1.
In this video, we're going to continue and complete our discussion of COOL's operational semantics. We'll be taking a look at the two most complex operations in COOL, the allocation of a new object and dynamic dispatch. We'll begin by giving an informal discussion of what happens when a new object is allocated in COOL. So the first thing that has to happen is we have to allocate space for the object, and essentially that means having enough space for the object's attributes. So we're going to have to allocate a location for every attribute of the object of class T if what we're doing is allocating a new T object. Then we're going to set the attributes of that object to their default values, and in a few minutes we'll say what the default values are and why we need to set the attributes to defaults. And then we evaluate the initializers. So every attribute in the class declaration can have an initializing expression, and we're going to evaluate those and set the resulting attribute values. And then we return the newly allocated object. So these are the steps that are involved in setting up a new object. And as you can see, it's actually more than just allocating a little bit of memory. It's actually quite a bit of computation going on in allocating new objects in COOL. Every class has a default value associated with that class. So for integers, the default value is 0. For Booleans, the default value is the Boolean false. And for strings, the default value is the empty string. And then for any other class that isn't one of these three basic classes, for any other class, the default value is void. In the operational rules, we're going to need a way to refer to the attributes of a class. So we're going to define a function called class that takes a class name and returns the list of attributes of that class. So here we have all the attributes of class A. Let's say they're A1 through AN. And in addition, this function is also going to tell us for each attribute the declared type of the attribute and the expression that initializes the attribute. And one other important feature of this list is that it includes all the attributes of class A, including the inherited ones. And there's another detail, which is in what order these attributes appear. And this will actually become important when we define the semantics of how attributes are initialized. And the rule is that attributes are listed in greatest ancestor first order. Okay, what do I mean by that? Let's say that we have three classes, A, B, and C. And B inherits from A, and C inherits from B. Okay, and let's say that A defines two attributes, A1 and A2, and B defines two attributes, B1, B2, and C defines two attributes, C1 and C2. Then class of C will list the attributes in the following order. First will come A1 and then A2, because A is the greatest ancestor. Okay, it's the closest to the root of the object hierarchy. And the attributes within class A, or within any class, are always listed in the order in which they textually appear. So first comes A1 and A2. And of course, the type and the initializer are also listed here for both of these attributes, but we're just concentrating here on the order in which the information appears. So then next would come class B. So the attributes of class B would be next. And of course, there would be the type and initializer for those attributes. And then finally, the attributes of class C, again, in the order in which they're listed in the class definition. Okay, so that defines the order of the attributes for any class. It's always in the order from greatest ancestor down the inheritance chain to the class itself, that is the argument of the class function. At this point, we're ready to actually define the formal semantics of new T. And let me switch colors here. So we're going to be allocating a new object of type T, and it's going to be in a context with self-object S0, environment E, and store S.